My name is Cian Murray. I'm a senior design engineer here at Arrotek Medical. So today I'm going to go through a steerable catheter and show some of the developments we do here at Arrotek and how we construct such a catheter. This would be an example of a catheter that is used for, say, mitral valve repair or some other similar clinical applications. It uses varying durometers in the jackets to give it a good bending characteristic and profile. And what we do is we use a stiffer jacket in the proximal section and then gradually work up to a softer durometer jacket in the distal end to focus that bending force onto the distal end of the catheter. We also have some varying braid PPIs and other technologies in this catheter to give it that smooth and targeted bending. In this catheter here, we have a one direction pull ring, which is welded in place with the braid. So we have laser welding capabilities in-house, and we can actually do braid terminations with the laser welding. So it removes the need for PET or adhesives in our distal end, and it also gives us good strength by bonding the braid to the pull ring. In this example, it's a single direction, single plane catheter, but we can work it in two directions in one plane, or we can add a second plane and go in four directions. This catheter, being a steerable, uses a braid reinforcement. So this one has a full load pattern, which is basically one wire over two and under two wires. So they crisscross and we can adjust the density on that as needed. It gives a good flexibility between pushability, kink resistance and torque transfer. But if we want to, say, go for different characteristics, we can use a diamond pattern. That would give a stiffer shaft and also give you better torque control and pushability. And it also has better kink resistance, but again, it's a stiffer shaft at the end, so flexibility wouldn't be the go-to on that one. We can also use a half load pattern, which is 8 wires instead of 16, and that'd be one wire over and under one wire. So that gives you great flexibility, probably the highest flexibility of any of the patterns. And it also gives you great adhesion because there's a higher amount of area under the braid that's exposed and allows your jackets to bond better to your liner. So if you're having delamination problems, maybe that's something you can look at. Some of the challenges with steerable catheters is we often look for a combination of mechanical properties. So how we overcome that is using various jacket durometers in one catheter length. So like I said, we can start with a stiffer durometer and move up to a more flexible durometer then at the distal end where it's needed. And we can also do some changes in the braid, so we can use different braid densities. So we can use a higher PPI in the proximal end where we want it stiffer, and then we could use a lower PPI or density on the distal end where we want more of that flexibility and trackability on the tip of the catheter.